The image that defines Chernobyl for the modern world is that immense, shimmering structure, the new safe confinement, a colossal steel arch built to slide over the ruins of reactor number 4. It is an engineering marvel, a testament to human determination to contain an apocalyptic mistake. But that arch is only the skin, the protective layer over the original wound. Beneath that sophisticated new shell, sealed away from the eyes of the world, lies the true, terrifying secret, the original structure known officially as the object shelter, or more commonly, the sarcophagus. This concrete and steel tomb, erected in the desperate aftermath of the 1986 disaster, is not merely a casing. It is the final resting place of a chemical and nuclear monstrosity, a complex maze housing materials that defy the known rules of physics and biology, materials that remain lethally radioactive even decades later. We often speak of the disaster itself, the evacuation, the human cost, but few truly grasp what was sealed away when the final steel beams were bolted into place. What is hiding in the perpetually dim, highly contaminated chambers deep within that original protective structure? The answers involve melted fuel, unmeasurable heat, structural instability, and silent, ongoing decay that has the potential to rewrite the geography of Eastern Europe if its secrets are ever fully exposed. We are about to delve into the depths of that concrete coffin, peeling back the layers of history, engineering, and almost unbelievable danger to finally understand the shocking reality sealed within the heart of the Chernobyl exclusion zone. If you find this journey into the most hazardous corners of history compelling, please take a moment to hit the like button and subscribe, so you don't miss any part of this deep dive into the secrets of the sarcophagus. The genesis of the sarcophagus is rooted in one specific, terrible night, the 26th of April, 1986. That night, the world learned the hard way about the inherent catastrophic flaw in the design of the Soviet RBMK-100 reactor, specifically the fatal positive void coefficient. What began as a misguided and deeply flawed safety test on the Unit 4 reactor spiraled instantly and violently out of control. When the reactor operators initiated the test, they set in motion a chain of events that culminated in two massive explosions that ripped the heart out of the facility. The first explosion was fueled by steam, generated almost instantaneously when the power surge caused the cooling water to flash into vapor. The pressure was unimaginable, tearing apart pipes and conduits. But it was the second, far more powerful explosion, fueled by the reaction of superheated steam and graphite, which physically ejected the massive upper biological shield steel plate weighing approximately 3,000 metric tons into the night sky. This wasn't just a structural failure, it was the total, catastrophic dismantling of the core containment, exposing the intensely radioactive fuel and the tons of burning graphite moderator to the open air. The immediate result was a plume of lethal radionuclides, shot miles into the atmosphere, carried by the prevailing winds across the Soviet Union and eventually across the European continent. The scene left behind was not merely a damaged building, it was an active nuclear inferno and a toxic lava flow. The roof and walls of the reactor hall were demolished, leaving a yawning, smoking cavity where the upper half of the unit used to be. The graphite blocks, ignited by the sheer heat and the infusion of oxygen, burned for days, raining down radioactive embers and continuing to emit a frightening amount of radiation. The initial response was heroic, reckless, and utterly desperate. Firefighters, unaware or tragically misinformed about the nature of the catastrophe, poured water onto the blaze, often facing radiation doses measured in Röntgens per hour, not per year. Helicopters flew mission after mission, attempting to smother the burning core with several thousand tons of materials: sand, clay, lead, dolomite, and boron carbide. The latter intended to absorb neutrons and prevent a renewed chain reaction. This aerial campaign partially succeeded in dampening the fire and suppressing some of the immediate aerosol release. But it also had an unintended consequence. The heavy materials, along with the melted uranium fuel and structural debris, created an incredibly dense, extremely hot mass that began to melt its way downward through the layers of concrete and steel beneath the core. The Soviet authorities realized immediately that the burning reactor represented not just an environmental catastrophe, but an existential threat. If the intensely hot, molten core material, now known as corium, continued its path downward and breached the concrete slab foundation, it risked entering the water table. Interaction with subterranean water or the basement reservoirs used for cooling could trigger a massive steam explosion, potentially throwing even more contamination skyward and rendering a vastly larger area permanently uninhabitable. The clock was ticking, and the priority shifted from fighting the fire to enclosing the entire structure. The object shelter, the future sarcophagus, was born from this frantic necessity. The goal was simple, yet demanded feats of engineering previously thought impossible. Build an impermeable barrier around the destroyed reactor core, sealing the radioactive materials, the burning fragments, and the melting lava flows inside. This barrier needed to be built quickly, durable enough to last for decades, and crucially, constructed remotely or by workers accepting suicidal levels of exposure. The construction of the original sarcophagus began just weeks after the explosion and was carried out in conditions that truly beggar belief. This was an operation managed by liquidators, a term given to the hundreds of thousands of military personnel, miners, engineers, and volunteers who converged on the site. Their task involved erecting structures in radiation fields where exposure limits were often surpassed in mere minutes. The engineering challenge was monstrous. They had to build a complex, multi-layered structure surrounding a core that was still emitting lethal radiation, where direct access was impossible. Many crucial elements of the sarcophagus had to be installed via cranes operated from a distance, or by custom-built heavy machinery, often remote-controlled, that quickly succumbed to the intense radiation, frying their electronics and rendering them useless. This failure of robotics meant that human hands, human bodies, had to complete the work. This desperate need led to the creation of the infamous biorobots, the 3,000 liquidators who rushed onto the reactor roof for 60-second shifts, shoveling radioactive graphite back into the core cavity, absorbing more radiation in those brief moments than any human should tolerate in a lifetime. Over a period of 206 days, between May and November of 1986, the sarcophagus took shape. It required the placement of more than 400,000 cubic meters of concrete and approximately 7,300 tons of metal structure. The structure was a haphazard collection of massive steel girders, concrete poured into makeshift forms, and specialized radiation shielding plates, all fused together in a high-stakes, high-radiation environment. The builders worked in 4 shifts, battling exhaustion, the lingering smoke, and the constant, invisible threat of ionizing radiation. They erected walls meters thick, designed to withstand not only the elements, but the incredible internal pressures and potential criticality events lurking inside the ruined core. The finished structure was immense, towering 50 meters high, covering an area the size of 2 football fields. Its primary function was burial, to isolate the ruins of Unit 4 from the environment, to contain the radioactive dust, and to provide a temporary shield until a permanent solution could be devised. When the sarcophagus was declared complete on November 30th, 1986, the world breathed a shallow, temporary sigh of relief. The beast was entombed. But the real question, the true foundation of the secrets hidden within, is, what exactly did they seal inside? The sarcophagus did not merely cover radioactive dust and burnt graphite. It sealed away the entirety of the reactor core and the terrifying products of its meltdown. When the explosion happened, the extreme heat caused the uranium dioxide fuel pellets, the zirconium cladding, the concrete shielding, and the steel supports to melt together into a viscous, intensely hot substance. This mixture, the corium, behaved like slow, radioactive lava. It flowed down through the massive pipes and channels of the reactor vessel, consuming everything in its path. Imagine liquid rock, radioactive beyond measure, tunneling into the foundation. This corium collected in the lower steam tunnels, pump rooms, and suppression pools beneath the reactor, forming new, solid masses with bizarre, glass-like structures. These unique formations were the most dangerous secrets sealed inside. They are not merely radioactive debris, they are solidified remnants of the core, still intensely hot, still emitting lethal radiation, and still capable of critical reactions if the internal conditions change. The sarcophagus, therefore, became a complex tomb containing not only the architectural ruins of Unit 4, but also tons of melted nuclear fuel that had rearranged itself into unstable formations. Engineers estimated that, inside that concrete shell, roughly 95% of the original nuclear fuel inventory remained. This immense quantity of fuel, along with highly radioactive fission products like cesium-137 and strontium-90, was not accessible. It lay buried deep within the lower levels, in formations that became known by various chilling names based on their appearance, such as the famous and terrifying elephant's foot. The sarcophagus was an attempt to manage an ongoing nuclear process, not merely a cleanup. It was a containment vessel designed to keep the volatile contents from interacting with the outside world, to prevent rain and snow from infiltrating the structure and potentially washing radioactive material into the soil, and crucially, to prevent the internal air from carrying radioactive aerosols outside the perimeter. The secrets of the sarcophagus are locked in the precise nature and location of these corium masses, their structural stability, and the radiation fields they continue to generate, forcing us to constantly monitor this concrete prison built in haste and consecrated by sacrifice. The foundation of this narrative is understanding that the sarcophagus was a compromise, a desperate bandage over a wound that never truly healed, only solidified and intensified. The true horror lies in the decades of decay and instability that followed its completion, which we must now explore. The initial construction of the hastily erected structure known as the object shelter, or, more commonly, the sarcophagus, was a feat of engineering driven by desperation and unimaginable risk. But to truly understand the secrets buried within that massive concrete and steel tomb, we must first peer into the abyss that the Soviet workers were trying to contain. We must look at what Unit 4 became in the immediate hours and days following that catastrophic rupture. Not just a destroyed building, but an environment unlike anything humanity had ever intentionally created. Inside the reactor vault, beneath the mangled remains of the reactor lid, known colloquially as the Alina, or the biological shielder monstrous, 1,000-ton pancake of metal and concrete now resting precariously lay the remains of the core. This was not simply a pile of rubble. It was a scene of active geological transformation fueled by nuclear heat. The temperatures in the heart of the core, even after the graphite fire had been partially suppressed, remained searingly high. The complex mixture of uranium fuel, the zirconium cladding that was meant to encase it, the steel of the reactor vessel, and the tons of concrete structural material that melted under the intense heat had begun to coalesce. This was the birth of corium, or more technically, the fuel-containing materials, FCMs. This substance is the shocking secret at the heart of the sarcophagus, a material so fundamentally alien and lethally dangerous that it dictated every decision made regarding containment. Imagine nuclear fuel, which typically resembles small ceramic pellets, being reduced to a molten, dense, and hyperradioactive liquid, mixing with the melted structural material of the building itself. This nuclear lava flowed downwards, burning and dissolving everything in its path, carving out paths of destruction through the steam tunnels, pump rooms, and cable shafts of the facility's lower levels. The corium was not uniform. Its appearance and composition varied depending on what it encountered on its journey downward. In some areas, where it encountered large amounts of silica from melted sand and concrete, it solidified into a dense, dark, glassy lava flow, often described by those who risked their lives to photograph it as looking like obsidian or hardened black tar. In other, deeper parts of the plant, particularly where it interacted with the vast amounts of water that had pooled in the lower corridors, water that had been used in failed firefighting attempts, the interaction was violent, leading to the formation of steam and potential criticality dangers. Crucially, the corium masses had to be precisely located and tracked, a process that required liquidators, equipped with crude shielding and rudimentary dose meters, to navigate crumbling, waterlogged, and highly radioactive mazes. Their reports indicated radiation fields so intense that even brief exposure meant a lethal dose. One of the most infamous and visually startling manifestations of this nuclear lava flow is the structure known worldwide as the Elephant's Foot. Located in a steam distribution corridor directly beneath the former reactor hall, this formation is a solid mass of corium, roughly the size of a small car. It is not named for its actual shape, though it does possess a rugged, wrinkled, organic appearance, but for the sheer weight and crushing density of the material. When first discovered and measured remotely in late 1986, the radiation levels near the Elephant's Foot were astronomical. They measured radiation doses that, depending on the precise location of measurement, could range from 8,000 to 10,000 Röntgens per hour. To put that into horrifying context, a dose of 400 Röntgens delivered rapidly is generally considered lethal. Even after years of decay, when the first human images of it were captured via robotics and carefully shielded cameras in the 1990s, the hazard remained profoundly high. The immediate danger of the corium, however, was not just its ability to instantly kill those who approached it. In the months immediately following the explosion, Soviet scientists and engineers grappled with the terrifying possibility of the molten fuel mass reaching the massive water-filled bubbler pools located directly below the core. Had the corium breached the concrete floor and contacted that large volume of water simultaneously, the resulting steam explosion could have pulverized the remainder of the containment structure and ejected massive amounts of highly radioactive material high into the atmosphere, potentially rendering vast swathes of Eastern Europe uninhabitable for centuries. This existential threat was the primary impetus for the heroic, often suicidal, efforts to pump the water out of the lower levels, a task famously carried out by miners and liquidators who dug tunnels beneath the plant to install cooling plates and drain the hazardous water. The corium, therefore, represented a persistent, active menace sealed within the sarcophagus. It was a shifting, unpredictable nuclear entity. As the material solidified, scientists worried about its long-term stability. Would the thermal stress cause the glassy matrix to shatter, releasing fine, highly mobile dust? Would the internal self-heating caused by the continued decay of fission products eventually lead to new melting, or perhaps a localized recriticality event? These concerns were not theoretical. They were the daily reality for the scientific teams monitoring the ravaged unit. The creation of the sarcophagus, the object shelter, was fundamentally a shield against these internal, invisible, yet profoundly deadly forces. The builders were not attempting a perfectly sealed containment. They were constructing a rapid, robust barrier against lethal radiation and against the further physical collapse of the reactor hall, which threatened to release even more radioactive debris. The construction timeline was brutally short, only 206 days from start to finish. This speed was achieved through immense sacrifice and led directly to structural compromises that would plague the structure almost immediately after its completion. Large sections of the reactor building had been blown away or severely damaged, leaving gaping holes and structural instabilities. The sarcophagus had to be anchored to the remaining fragments of the destroyed structure. This meant that the resulting shelter was not a solid, uniform envelope. It was a patchwork assembly of thick concrete walls, steel beams, and prefabricated panels dropped into place, often with limited visibility due to the high radiation fields. The western wall, for instance, had to be built with a deliberately staggered design, avoiding the most radioactive debris heaps. The roof was essentially a series of huge, prefabricated steel sections dropped onto supporting structures. The problem, inherent in the rushed and dangerous conditions, was that the fit was never perfect. Large gaps, cracks, and fissures remained open, some visible, others hidden high up in the roofline. These gaps served two immediate, critical functions. Firstly, they allowed water infiltration, leading to corrosion and the washing down of radioactive materials into the lower levels, concentrating the contamination. Secondly, and perhaps more ominously for the engineers, they prevented the sarcophagus from ever being truly hermetically sealed. Air was able to circulate, carrying radioactive dust particles out into the environment, albeit at a reduced rate compared to the immediate post-explosion phase. Within months of its completion in November 1986, the object shelter began to show signs of structural distress. The primary supports, weakened by the original blast and subject to continuous thermal and radiological stress, were settling unevenly. Cracks began to appear in the concrete walls. The most alarming discovery, however, was the instability of the massive concrete and steel components that the sarcophagus was designed to contain. Specifically, the remains of the reactor hall walls and the biological shield, that 1,000-ton slab, were deemed dangerously unstable, leaning precariously on degraded structures. The structural secrets buried within the sarcophagus were therefore dual: the lethal, solid masses of corium that promised death to anyone who ventured too close, and the crumbling, compromised structure built around them. The initial goal had been met, containing the immediate release of radioactivity and stabilizing the area. But the long-term reality was that the sarcophagus was not a permanent solution. It was a temporary coffin, already decaying and threatening to collapse onto its own radioactive contents. This instability created the profound, multi-layered problem that future engineering efforts would have to solve: a battle against time and the invisible forces of decay and radiation that were slowly eating away at the world's most dangerous architectural creation. We continue our descent into the physical and chemical nightmare that coalesced beneath Reactor 4. The immediate goal of the liquidators, once the explosion was contained and the initial fires were smothered, was not to clean up the fuel, but simply to cap the geyser of radiation and stopped the catastrophe from becoming truly planetary. But capping the volcano only hid the magma. What remained inside the hastily erected shelter structure, the sarcophagus, was an entirely new geological formation, a product of nuclear alchemy unlike anything seen before. This formation is known as fuel-containing material, or FCM, and its primary, and most chilling, constituent is corium. Corium is not just melted nuclear fuel. It is a glassy, ceramic blend incorporating the fuel uranium dioxide, the reactor's structural metal, zirconium, alloys, and steel, the cooling water, and the very concrete floor of the reactor hall that it melted through. Imagine a volcanic eruption where the magma is intensely radioactive, mixed with the scorched remains of the industrial facility it consumed. The creation of this corium was a process of intense heat, rapid chemical reactions, and subsequent cooling, which resulted in structures of terrifying density and complexity. The corium flows did not behave uniformly. When the core melted, the mixture flowed downward, encountering the concrete baseplate. The immense heat, estimated to be well over 2,000 degrees Celsius, vaporized the moisture in the concrete and caused the silica and calcium components to fuse with the molten uranium and zirconium. This interaction created different textures and compositions. Some flows, particularly those far from the main core mass, solidified into glassy, amber, or brown-colored lavas, almost beautiful if they weren't lethally toxic. Other areas, where the fuel concentration remained highest, formed dense, dark, ceramic masses that settled in pools. The most infamous example of this process is, of course, the elephant's foot, found in room 305 halves. But the elephant's foot is merely the largest, most visually striking sentinel of a much vaster network of solid, radioactive lava flows that snake through the lower levels of the reactor building. These subterranean streams of decay extend for dozens of meters, filling pipes, conduits, and ventilation ducts. They are not merely superficial deposits. They have integrated themselves into the very structure of the building, forming new, permanent radioactive foundations. Sampling these materials proved a nearly impossible task for the scientists and engineers who first dared to enter the sarcophagus decades ago. The radiation fields were, and in many places remain, so intense that even remote monitoring equipment failed or registered off the scale. When physical samples were finally retrieved, often using highly shielded, long-handled remote tools, they revealed the corium's almost granite-like toughness. The material is incredibly dense, resistant to acid, and structurally harder than many natural stones. This hardness is crucial because it means the material will not simply dissolve or erode easily. But it also means that future decommissioning efforts requiring its removal will be excruciatingly difficult, necessitating specialized cutting tools and remote manipulation far beyond standard demolition technology. Furthermore, the corium is not chemically inert. While it has cooled considerably since 1986, the decay heat from the remaining radioactive isotopes ensures that the material still maintains elevated temperatures, particularly in the most massive formations. This internal heat contributes to structural degradation around the corium, drying out and cracking the remaining concrete infrastructure. The heat also complicates the long-term threat by interacting with any moisture that penetrates the crumbling sarcophagus, creating steam and potentially increasing the internal humidity, a factor critical to the second major secret hidden within the structure: the risk of renewed subcriticality. The threat of a secondary, small-scale nuclear reaction lurking within the melting core material is a constant, spectral worry for the custodians of Chernobyl. We are not talking about a major explosion like the one in 1986. which was a runaway power excursion fueled by steam and graphite. Instead, the concern centers on localized, self-sustaining nuclear chain reactions, known as criticality events, occurring within the highly concentrated corium masses. For nuclear fuel to undergo fission, the neutrons released by decaying atoms must be slowed down so they can strike other fissile nuclei like uranium-235, sustaining the reaction. In the original RBMK reactor, graphite acted as the primary moderator, slowing down the neutrons. After the meltdown, however, the structure changed. The corium contains the fuel, but it is often intermixed with water or hydrogen-containing compounds which, in this new configuration, can act as effective moderators. The primary enemy here is water. If the highly enriched, dense masses of corium which have been drying out over the decades suddenly become saturated with water, the neutron moderation efficiency drastically increases. This saturation is entirely possible due to the structural flaws of the original sarcophagus. Rainwater and snowmelt continually infiltrate the damaged concrete and steel structure, trickling down into the lower radioactive halls where the corium resides, especially rooms like 305 halves and 304 thirds. In the late 1990s and early 2000s, scientists monitoring the neutron flux within the sarcophagus observed spikes, momentary, localized increases in neutron counts that strongly suggested the onset of subcritical reactions. These transient reactions, or neutron bursts, happen when infiltrating water collects in a cavity containing enough highly concentrated fuel, momentarily increasing the fission rate before the heat generated boils the water off, ending the moderation and shutting the reaction down. While these events were brief and did not pose a massive explosion risk, they were a stark, terrifying reminder that the fuel was still dynamically capable of fissioning. It was, in effect, a sleeping dragon that occasionally snorted radioactive fire. The solution developed to counteract this threat was the highly complex and dangerous operation of spraying neutron-absorbing solutions, primarily containing boron, into the inaccessible zones. Boron acts as a neutron sponge, capturing the neutrons before they can perpetuate a chain reaction. However, delivering the borated liquid was a Sisyphean task. Many of the most hazardous zones, the basement areas where the largest amounts of corium settled, were sealed off by meters of hardened debris or structurally unstable access points. Workers had to drill holes, sometimes hundreds of feet long, through thick concrete barriers, often relying on imprecise maps and remote video feeds, simply to insert nozzles and spray the solution blindly into the high radiation zones. This effort required immense logistical coordination and exposed teams to significant risk. The work was never conclusive. The battle against water infiltration is ongoing, and the potential for a localized criticality event remains a persistent low-level threat until the fuel is permanently isolated or removed. The very structure meant to contain these hazards, the original sarcophagus, or the shelter structure, is, in itself, one of the most immediate and terrifying secrets of Chernobyl. It was a heroic feat of engineering, built in a desperate 6-month sprint under impossible radiation conditions, but it was a temporary solution designed to last perhaps 20 to 30 years, built with compromised materials and necessarily imprecise measurements. The result was a structure riddled with inherent, fatal flaws. One of the most critical structural weaknesses lay in the massive beam known as the Mama beam, which supported much of the roof structure directly above the hottest debris. This beam, placed under immense stress during the construction process, was never fully anchored in a way that guaranteed long-term stability. Furthermore, the sheer, uneven load of thousands of tons of concrete and steel, placed quickly on a building already heavily damaged and warped by heat, meant the sarcophagus was continuously settling and shifting. The most dangerous consequence of this rapid, improvised construction was the presence of significant cracks, gaps, and structural openings. These openings not only facilitated the water infiltration that stoked the criticality risk, but also allowed for the continuous release of highly radioactive dust and aerosols into the immediate environment. The sarcophagus was not airtight. It was a glorified, crumbling lid on a pressure cooker of atomic debris. Wind could blow through the cracks, carrying contaminated dust from the pulverized graphite and fuel particles that settled in the reactor hall. Engineers estimated that any major collapse of the sarcophagus, an event increasingly probable as structural elements corroded and rusted due to water penetration, could cause a massive release of highly contaminated dust. This dust, which includes not only pulverized concrete and graphite but also fine particles of corium, was estimated to weigh several hundred tons. A collapse scenario was not just a structural failure. It was a potential localized radiological disaster, capable of contaminating an area far beyond the immediate exclusion zone, depending on wind patterns. This imminent danger of collapse was the single greatest driver for the subsequent international effort to build the new safe confinement, or the NSC, the massive arch structure that now dominates the Chernobyl skyline. The sarcophagus was living on borrowed time. Engineers had identified specific structural elements, including the aforementioned mummer beam and certain wall supports, that were degrading at an alarming rate. Any significant earthquake or even a severe snow load could have been the trigger for a catastrophic structural failure. Before the NSC could be slid into place, an entire internal stabilization project had to be undertaken. Workers had to brace the most vulnerable sections of the old structure, working within the high radiation fields to ensure that the sarcophagus did not collapse during the construction and maneuvering of the new arch. This bracing, known as the stabilization measures, was a testament to human ingenuity and risk tolerance, providing a temporary lifeline to a structure that was literally tearing itself apart under the weight of history and radiation. The secrets hidden within the original sarcophagus are thus multifaceted. They involved the creation of lethal, artificial minerals, corium, the constant threat of renewed, localized nuclear reactions, criticality events driven by water, and the terrifying structural decay of the containment measure itself. All these factors combined to present a scenario of perpetual danger, requiring constant surveillance and monumental engineering solutions to transition the containment from a temporary cap to a long-term, stable isolation facility. The core problem, however, remains. The fuel is still there, highly reactive, intensely hot, and structurally integrated into the very ruins of the building that birthed it. And the monumental task of addressing this deep secret is still many decades away from conclusion. The decaying heart of reactor number 4, sealed hastily within the concrete confines of the shelter object, the original sarcophagus, was never intended to be a permanent solution. It was a desperate bandage applied to a catastrophic wound, a shield constructed in 5 short months under unimaginable radiological duress. But as the frantic urgency of 1986 receded into the slow, grinding reality of the post-disaster decades, the terrifying truth about the sarcophagus began to emerge. It was failing, degrading daily, turning the temporary containment into a ticking time bomb of structural decay and radiological threat. Inside that collapsing concrete shell lay not just the ruins of a building, but a geological anomaly, a secret world forged in the extreme heat of a nuclear runaway chain reaction. The central mystery, the shocking secret buried beneath layers of twisted rebar and dusty concrete, was the corium, the fuel-containing materials, or FCM. This was the liquid core of the reactor. The uranium dioxide fuel mixed with zirconium, graphite, steel, and the pulverized concrete foundations all melted together into a dense, non-natural ceramic lava. Scientists and engineers, working in short, dangerous shifts, gradually mapped the interior landscape of this newly formed nuclear geology, revealing structures that defied imagination. The most infamous of these formations, and perhaps the single most potent symbol of the hidden dangers, is the structure famously dubbed the Elephant's Foot. Located deep within the steam distribution corridor beneath the reactor vessel, this mass is deceptively benign in appearance, a dull, solidified flow, slightly iridescent, resembling dark volcanic glass, or perhaps the foot of a massive elephant. Its texture is ridged, flowing, demonstrating the incredible fluidity the material possessed as it burned through everything in its path. But its appearance belies its toxicity. When it was first discovered and measured remotely, the radiation levels emanating from the elephant's foot were so high, often exceeding 8,000 roentgens per hour in the early years, that merely standing near it for 30 seconds was a death sentence. To put that in perspective, a lethal dose for a human is often measured in hundreds of roentgens. This one formation, only a few cubic meters in volume, held the accumulated, consolidated fury of the destroyed reactor core. However, the corium did not manifest in a single, monolithic mass. As the melted fuel flowed and reacted with different components, it solidified into distinct phases. There were the black, glassy lavas, often highly dense and situated in the lowest points. Then there were the porous, yellowish-brown formations, looking like stalactites or stalagmites, sometimes referred to as icicles, hanging from horizontal surfaces. These formations were the result of the molten material mixing with concrete aggregates like sand and limestone, creating a complex silicate matrix. The heat was so intense, reaching temperatures well over 2,000 degrees Celsius, that it facilitated a process known as vitrification, trapping the highly radioactive fission products, including cesium-137 and strontium-90, inside a glass-like solid structure. This accidental vitrification was, in a strange twist of fate, a primitive form of long-term waste storage, albeit one that was highly precarious and situated right beneath the destroyed reactor building. The true concern surrounding the corium was not simply its current high level of radioactivity, but its long-term potential for instability and criticality. The corium still contains a significant percentage of the original uranium, fuel estimated to be around 10% of the mass, meaning it is still fissile material. While the material is currently in a subcritical state, the neutrons are not multiplying enough to sustain a reaction. The introduction of water is the great unknown variable. Water acts as a moderator, slowing down neutrons and potentially making the fissile material more efficient at sustaining a reaction. If enough water were to penetrate the sarcophagus and accumulate around a specific geometry of corium, it could, theoretically, cause a localized critical excursion, a release of heat and radiation that could generate steam pressure, potentially scattering radioactive dust throughout the containment structure and into the atmosphere. This perpetual fear of water ingress, driven by rain and snow filtering through the damaged roof of the sarcophagus, necessitated constant, intrusive monitoring and, crucially, the application of neutron absorbers like gadolinium nitrate solution directly onto the most suspicious corium formations deep within the ruins. Simultaneously, while scientists probed the dangers below, engineers grappled with the dangers above. The sarcophagus structure, hastily built with 400,000 cubic meters of concrete and 7,300 tons of metal structures, was inherently unstable. Key support beams, like the colossal Mammoth beam, spanned great distances and were subjected to intense thermal stress, radiation damage, and differential settling of the reactor building foundation. By the late 1990s, serious flaws became apparent. Gaps and cracks had formed, allowing significant amounts of precipitation and air to enter and exit. This allowed the highly radioactive dust, accumulated on surfaces and trapped in the upper debris, to be mobilized by wind or water, threatening to escape the confinement. Furthermore, several large segments of the upper concrete structure, including the so-called Schema E segments, were precariously balanced and had zero safety margin against collapse. A collapse would not only create an immediate, massive release of radioactive dust, but would also smash into the corium formations below, potentially altering their geometry and triggering the feared criticality event. The original sarcophagus, intended to last perhaps 20 to 30 years, was deemed to be at imminent risk of failure by the turn of the millennium. The structure was assessed to have a greater than 150 square meter opening in its roof and walls, rendering its containment function severely compromised. It became abundantly clear that the only way to mitigate the profound long-term risks posed by the collapsing sarcophagus and the volatile corium inside was to build an entirely new structure, a permanent, robust shield capable of lasting a century and, critically, allowing for the eventual, systematic deconstruction of the original failed containment and the cleanup of the reactor building ruins beneath. This monumental task gave birth to the design and subsequent construction of the new safe confinement, ORNSC, often referred to simply as the Arch. The NSC project was not just an engineering feat. It was a political and logistical triumph requiring massive international collaboration. The sheer scale of the funding required over €2 billion necessitated contributions from 45 donor nations and organizations, coordinated primarily by the European Bank for Reconstruction and Development. The mandate was clear: design a structure robust enough to survive extreme weather, stable enough to last 100 years, and, most challenging of all, build it away from the immediate contamination zone and slide it over the existing failed structure. The engineers tasked with designing the arch faced constraints that were unprecedented in civil construction history. How do you build the world's largest movable land structure that dwarfs the size of the Astrodome, standing 108 meters high, 274 meters wide, and 162 meters long in a highly volatile and radiologically compromised environment? The answer was revolutionary. The arch had to be constructed in sections in a clean zone, approximately 300 meters west of reactor number 4. This shielded construction zone allowed workers to operate under normal safety protocols, minimizing their radiation exposure dramatically. The specifications were exhaustive. The arch needed to withstand high winds, seismic activity, and the corrosive environment caused by the dust and moisture trapped beneath. Its design was a marvel of modern engineering, utilizing a double-skin system, akin to a massive thermos flask, designed to maintain positive air pressure between the skins. This continuous positive pressure ensures that if any breach occurs in the structure, the airflow is always directed inward, preventing any potential radioactive particles from escaping the containment into the atmosphere. Furthermore, the NSC was not merely a passive shelter. It was conceived as an active remediation tool. The interior of the arch houses a vast array of sophisticated, remotely operated equipment, most notably 2 massive overhead cranes with a carrying capacity of 50 tons each, and specialized dismantling tools. These systems are designed to eventually reach down through the protective envelope of the NSC and begin the slow, methodical process of taking apart the crumbling sarcophagus and, eventually, accessing the corium formations themselves for final disposition. The goal is not just containment, but irreversible cleanup. The arch is the workshop for the next 100 years of decommissioning, providing the vital radiological shielding necessary for human intervention to finally address the shocking secrets hidden within the destroyed reactor core. The sheer mass of the structure, 36,000 tons of steel, presented the ultimate challenge, moving it. Once construction was completed in the safe zone, the entire arch had to be slid over the existing sarcophagus. This was the final, defining act of the initial construction phase, relying on a sophisticated hydraulic jacking system. Moving a structure of this scale, slowly, deliberately, over 300 meters, was a process that captivated the world and underscored the gravity of the nuclear legacy that required such a colossal response. The arch truly represents the acknowledgement that the secrets hidden beneath the original sarcophagus, the unstable structure, the volatile corium, and the ever-present threat of criticality demanded a solution commensurate with the scale of the disaster. The final act of the Chernobyl disaster was not a flash of fire, nor a catastrophic explosion of steam, but rather a slow, monumental engineering effort focused on putting a lid on the fury that continued to burn silently. The original sarcophagus, hastily constructed in 6 months in 1986, was, at best, a temporary solution. It was erected with heroism and desperation, using robots and helicopters, but it was born with critical structural flaws, holes through which radiation leaked, and a projected lifespan of no more than 30 years. As time passed, the most secretive and perhaps most fatal threat was the imminent structural collapse that could raise clouds of radioactive dust and expose the world once again to the trapped toxic contents. It was a silent countdown. The ultimate truth, the secret that had to be confronted, wasn't mutant monsters or inexplicable phenomena, but brutal physics and slow decay. The construction of what became known as the New Safe Confinement, or NSC, was our collective admission that the Chernobyl problem wouldn't solve itself in a generation or two. The NSC is the 21st century's answer to the 20th century catastrophe, a massive steel arch, 108 meters high, 274 meters wide, and weighing over 36,000 metric tons. Imagine the world's largest aircraft hangar, but built to contain hell. The decision to build the NSC was an acknowledgement that the sarcophagus was failing. The roof, in particular, was a cause for grave concern. The supporting beams, exposed to unbelievable levels of radiation and corrosion, were weakening. The fear was that a collapse could crush the remnants of reactor number 4 and launch highly pulverized fuel dust, spreading radioactive material for miles. It wouldn't be a 1986 scale event, but it would undeniably be disastrous for Europe and for containment efforts. The NSC, nicknamed the Arch, was designed to be built away from Reactor 4, in a safe area, and then slid over the existing structure. This construction technique, a remarkable feat of civil engineering, eliminated the need to expose workers to lethal doses of radiation during assembly. The final sliding of the arch, completed in 2016 and commissioned in 2019, was a moment of relief and technical triumph. It was not just a cover, it was a structure designed to last at least 100 years, giving humanity time to dismantle the remains of the sarcophagus and, crucially, deal with the molten fuel hidden within. The NSC, by sealing Reactor 4, revealed a long-held secret that has become the focus of intensive monitoring: the ongoing threat of melted uranium fuel. now transformed into fuel-containing material, or FCMS, beneath the NSC remains a vast and complex landscape of solidified lava, radioactive dust, and core fragments. The exact amount of fuel is still debated, but the most widely accepted estimate is that about 95% of the original fuel, approximately 170 to 180 metric tons, is trapped within the ruins and corium formations. The elephant's feet, that monstrous dark mass of corium in the steam corridor, has become the visual emblem of radioactive persistence. But the NSC isn't there just to protect against the elephant's feet. It's there to protect against the thousands of tons of debris and tanks of pulverized fuel scattered throughout the lower chambers. The most troubling secret that the NSC helps monitor is the chemical and physical evolution of these FCMs over time. As the NSC created a hermetically sealed environment, a new danger arose: the possibility of water re-entry. The original sarcophagus, with its cracks and holes, allowed rain to enter and flow in, washing away radioactive materials, which was dangerous, but it also kept the materials dry. Water is the #1 enemy of corium. Why? Because decaying uranium within corium has an extremely low probability of initiating a fission chain reaction, i.e., a critical state, if it is dry. However, if moderated by water, which acts as a neutron brake, allowing neutrons to strike the uranium at ideal speeds for fission, the probability of a chain reaction increases exponentially. With the NSC installed, the water leakage problem was drastically reduced, but internal humidity became a factor. Monitoring teams, using probes and remote sensors installed before the completion of the arc, began to observe worrying fluctuations in what is called neutron flux. This is the most tense and current secret lying beneath the NSC: neutron spikes. In certain hard-to-reach spots, particularly in some of the fuel storage rooms and under the remains of the bubbling pool, slow and persistent increases in neutron flux have been detected. This suggests that as rainwater seeped into small cracks in the corium before the NSC's completion, or as moisture accumulated, the radioactive material was becoming more reactive. In 1990, scientists had already injected gadolinium nitrate, a neutron absorber, into certain areas to avert criticality. However, the threat never disappeared. The discovery of neutron spikes, which are monitored by a complex array of detectors, does not mean that a nuclear explosion is about to occur. However, it does mean that there is the potential for an uncontrolled criticality event, which would release intense heat and, more dangerously, intense radiation, damaging containment systems and possibly causing further structural damage. This requires ongoing active intervention. Containment teams, now protected by the NSC, continue to look for ways to remotely inject neutron absorbers into these hot areas, often using robots or drilling through the remains of the structure to reach the material hidden beneath meters of destroyed concrete and molten debris. The real conclusion about what lies hidden inside the sarcophagus, now covered by the NSC, is this: it is not an empty vault, nor a sterile chamber. It is a gigantic vessel of dismantled reactors, filled with material that is changing shape. The FCMs are slowly pulverizing. They are transforming from glassy lava into fine, unstable dust, a process accelerated by radiation and decay. If this dust is disturbed and inhaled, it represents an extreme radiological risk. This is the second great secret that the NSC protects. It stabilizes the environment so that this dust does not spread. Radioactive dust, mixed with corium, is at the heart of the dismantling problem. The ultimate purpose of the NSC is not only to seal the site, but to allow teams to use cranes and robotic tools inside the structure to eventually dismantle the original sarcophagus and extract the corium piece by piece. This is a demolition project that will take decades, if not longer, and the process of separating and packaging the fuel material is itself an unprecedented technical and radiological challenge in the history of nuclear engineering. The legacy of Chernobyl and the definitive conclusion of this story lies in its transition from an acute disaster to a chronic, intergenerational challenge. The NSC is a promise that we will not forget the risks and that we will dedicate the necessary resources to dealing with the reactor's remains for at least another century. It is the largest land-based structure ever built to contain an industrial hazard. The final secrets of Chernobyl are not shocking in the sense of being unexpected, but rather shocking in their persistence and timescale. What lies hidden there is uranium-235, plutonium-239, and a myriad of long half-life isotopes, such as cesium-137 and strontium-90, which will continue to emit dangerous radiation for tens of thousands of years. The ultimate irony of the Chernobyl story is the exclusion zone. While the center of the disaster is sealed off with high-tech steel, the surrounding forest thrives, creating a wildlife sanctuary that is dangerous but ecologically rich. The area has become an unwitting laboratory for how nature reacts when human pressure is drastically removed. Yet, even as wolves, moose, and lynxes roam freely, the mark of radiation remains in the soil and sediments. The sarcophagus, now a shadow beneath the new safe confinement, served its purpose, buying valuable time. It kept the worst of the radioactive furies under control until the world could unite to fund and build a long-term solution. The NSC, in its majestic scale, is as much a monument to nuclear failure as it is to human tenacity. It closes the story of the immediate catastrophe, but opens the chapter of long-term radioactive management. So, what was really hidden inside? Hidden within was proof that even the most destructive and uncontrollable power, the fury of a reactor core, can be confronted and eventually sealed by steel and human intelligence. The secrets are composed of uranium silicate, plutonium oxides, and the constant threat of neutron criticality moderated by water. It is a secret of physics and engineering, a burden that humanity will carry for generations, ensuring that what lies within reactor number 4 remains encapsulated and under control. The story of Chernobyl is a cycle of destruction, containment, and relentless vigilance. Every day, the sensors inside the NSC send data, and the work continues, a silent testament to the cost of nuclear energy. If you found this journey into the core of Chernobyl informative and revealing, consider liking and subscribing for more in-depth analysis of the events that shaped modern history. The work of documenting and understanding the Chernobyl disaster never ends, and your curiosity helps us maintain vigilance.